Good morning, everyone. I am Engineer Paula Maril Ababaw from FEU Institute of Technology, Philippines. Today, I will be presenting our paper titled Review of Artificial Intelligence Applications in Performance Prediction of Advanced Energy Materials, co-authored with Engineer Ian Benitez. This presentation explores how artificial intelligence is transforming computational material science, particularly in the context of sustainable and advanced energy technologies. We will look at where we are now, what has been achieved, and the challenges and opportunities that lie ahead. Why energy materials matter. Energy materials are critical because they form the building blocks of sustainable energies. Batteries, fuel cells, and electrolyzers depend on advanced materials to function efficiently, reliably, and at scale. Traditionally, the discovery and optimization of new materials takes 10 to 20 years. For example, lithium batteries took decades from concept to commercial adoption. This trial and error process is slow and costly, involving thousands of experiments. This bottleneck makes it difficult to respond to urgent challenges like the climate crisis, so we need faster ways to identify and test promising materials, and this is where AI can play a transformative role. AI helps shorten this timeline dramatically. Instead of decades, discovery cycles can be produced in just a few years or even months. Traditional approaches like density functional theory or DFT are accurate, but they are computationally expensive and impractical for large-scale screening. AI, on the other hand, learns patterns directly from data, enabling rapid predictions of properties like stability, conductivity, or catalytic activity. The most exciting aspect is the closed-loop design cycle. AI predicts materials properties, experimentalists validate them, and the data feeds back into the model, improving it continuously. This synergy between AI and experiments accelerates innovation in unprecedented ways. Our first objective is to survey and evaluate AI applications in performance prediction of advanced energy materials. Second is to compare different AI models from simple regression models to deep learning architectures like graph neural networks in terms of accuracy, interpretability, and data efficiency. And lastly is to outline future directions and research gap, focusing on how AI can be further integrated into materials discovery pipeline. By doing this, we hope to provide a clearer picture of where AI is succeeding, where it still struggles, and how researchers can better harness its potential. Our methodology began with a systematic literature survey of peer-reviewed articles in the Scopus, Web of Science, and Google Scholar. We used keywords such as AI for batteries, machine learning in fuel cells, graph neural networks, and so on. And we extracted the data including the type of AI model, target property, data size, and the performance metrics such as RMSE or R squared. This allowed us to create a structured comparison across different domains, from battery performance forecasting to catalyst activity prediction to fuel cell degradation modeling. By categorizing these studies, we could highlight trends, identify the most promising approaches, and uncover common limitations. AI has found applications across full spectrum of energy materials. In batteries, machine learning is used to predict cycle life and capacity fade. For instance, Tesla has applied AI models to forecast battery degradation in limited charge-discharge cycles. In fuel cells, AI models predict proton conductivity or catalytic activity, helping design more durable membranes and efficient catalysts. And in electrolyzers, AI accelerates the search for low-cost, stable electrocatalysts for water splitting, especially for hydrogen production. What we observe is that AI doesn't replace experiments but makes them more targeted, reducing the search space so researchers spend less time on dead ends and more on promising candidates. AI versus trial and error in fuel cell development. This figure shows a comparison between traditional trial and error approaches and AI-guided development in fuel cells. Traditionally, thousands of iterations are required before identifying a promising material, and often this process takes more than a decade. AI shortens this cycle by predicting performance from synthesis. For example, rather than testing 1,000 candidate catalysts, AI may narrow the search to the top 10 most promising ones. This dramatically reduces wasted time and cost. In practical terms, what once took 15 years can now be accomplished in 2 or 3 years. Different AI models have their strengths and weaknesses. Tree-based models like Random Forest or XGBoost are highly efficient with small datasets and offer strong interpretability. Deep neural networks perform well with large datasets but risk overfitting when data is scarce. Graph neural networks are particularly powerful for materials because they can encode the atomic and structural information of compounds. The key insight here is that there is no universal model that works best for all cases. Model selection depends on the property of interest, data size, and whether interpretability or predictive accuracy is the priority. Despite the progress, there are still major challenges. First, data scarcity. Most experimental data in materials science is not FAIR, findable, accessible, interoperable, and reusable. Many datasets are too small, noisy, or biased, which reduces the reliability of AI predictions. Second, interpretability. Many AI models are black boxes, where experimental scientists, it's not enough to know that what the model predicts a high activity. They also want to understand why. This lack of transparency reduces adoption and trust in AI systems. One promising solution is physics-informed machine learning, which integrates domain knowledge and physical laws into AI models. This not only improves accuracy but also provides more interpretable results. Another limitation is generalizability. Models trained on one material class often fail when applied to others. A model that works well for nickel-based catalysts may not generalize to iridium-based ones. There is also the issue of sustainability in AI itself. Training large deep learning models consumes significant energy, sometimes producing as much as CO2 as multiple car lifetimes. This creates a paradox. We use AI to support green energy transitions, yet its own footprint can be environmentally costly. The way forward is to design more data efficient, lightweight models and adopt greener computing practices so that AI remains aligned with sustainability goals. Looking to the future, we can see three major stages. In the next 5 years, AI will be mostly impactful in rapid screening and prioritization of candidate materials. In 10 years, we expect to see digital twins, virtual models of real experimental systems that can simulate material behavior under different conditions. And in 20 years, we may witness fully autonomous laboratories where AI not only designs and simulates, but also directs robots to synthesize and test new materials in a continuous closed loop. This vision of self-driving labs represents the ultimate integration of AI and experimental science. For the conclusion, AI significantly accelerates materials discovery, reducing cycles from decades to just years. Different models have different strengths: tree-based models for small data, deep learning for large datasets, and graph networks for structured data. Limitations persist in data availability, interpretability, and generalizability. The future lies in hybrid approaches, physics-informed AI, digital twins, and eventually autonomous laboratories. Ultimately, AI will not replace human scientists but will become an indispensable partner in the quest for sustainable energy solutions.